language processing aims to design algorithms that will analyze, understand, and if necessary, generate natural language automatically. And there are many electronic data resources available online, like Topkara, for example, Wall Street Journal text, or corpus means a long text that is a representative of a language. There are many electronic dictionaries like WordNet or VerbNet, or off-the-shelf parsers, generators, machine translation tools can be used to create a watermarking system. I will tell you a little bit about the previous approaches. There are two different ways of performing information hiding into natural language text. One way is you can generate the cover text. It is usually used for steganography because the text doesn't have any value. So you give me a message, and I just generate a spam email, like in the case of Spam Mimic. If you go to spammimic.org, you type in your message and it creates a spam email for you. And you can send it to your friend. It will look like a spam email sent by you, but in fact it has a message inside it. But the other case that we deal in watermarking is modifying a cover text, which is a little bit harder because we have an active adversary who wants to remove our watermark or insert his watermark on top of our watermark. These techniques that are proposed for given cover text, it can also be used for steganography as well because you're inserting a message. This is a steganography example. I told you about Spam Mimic. This is a very classic example. So this is by Weiner, proposed in '92. What you do is this is the message. If you can see my mouse, this is the message we want to insert, and this is a probabilistic context-free grammar. Every rule in the grammar has a special code. And what we do is we start from the beginning and try to insert this rule and generate a sentence at the end. Insert this message and generate a sentence at the end. So we start with the S rule and we look for one. Here. And we go with the rule that is using SCB, and then we need to insert the sequence that is starting with 0, 1. So we go for C and we pick everybody B because it is the 0 encoding, and we continue this until we fill in all the we put in all the message and we get the sentence everybody wants pie. This is what is behind the Spam Mimic tool. Another work from natural language watermarking. In fact, this work is coming from Purdue. Here, there are two approaches that is proposed in order to perform sentence-level watermarking. The first approach was using a syntactic parser, create a syntactic parse tree of a sentence, which you can see here. Ned loves Jody. This is a tree, in fact, you can use the parentheses to create the leaves. And the system proposed by Professor Atala and Professor Askin here and a group of students, we want to change the tree so that the encoding, the bit string that we will assign to the nodes of the tree changes. And the reader later will assign the same labels to the tree and read the bit string to detect the message, to extract the message out of it. Same idea was used in the second work, the semantic-based one, but the tree was different here. It was the text meaning representation. You're using the semantic parse tree of the sentence, which is here you see the parse tree of this sentence, and here the transformations are semantic, meaning-based transformations. This tool is more powerful than the first one because if you change the meaning of the text without in fact changing the full meaning of the text, it can even survive through translations. In fact, I was part of this work when I came here in my first year. You cannot really see, but we published a paper. It's okay. The black is not. So there are a couple of names here, probably recognizable to you. We published a paper at Information Hiding Workshop in 2002 that is about the semantic-based watermarking. I'll tell you more about our recent approaches. You can provide resilience to remove a text in two ways. One of them is really using obscurity. You are hiding the information carriers through the sea of many sentences. For that, we propose sentence-level watermarking, or you can make it really hard to undo the embedding changes for the attacker. And that one is the second and the third work that I will tell you about. The system that, like, we name our system as Enigmark. This is based on linguistic transformations that are defined over a sentence. I'm paraphrasing a sentence, for example. I'm not looking at information carriers at the word level, but I'm looking at them at the sentence level. Because we wanted to use the sentences because it provides a large feature space, and we need a larger feature space because our watermarking algorithm is based on orthogonal features. We want the features that we used for selecting who will be the information carrier be orthogonal to the features that we are using for embedding. For example, my system picked this sentence because it has the words frank and close. For some reason, it was looking for this for the selection, but I can rewrite this as this chapter will be closed by this frank discussion, and my embedding feature would be the number of prepositions in the sentence, which I change by doing this transformation. Or I can change it in another way. When I say this chapter by this frank discussion will be closed, I even change the number of punctuation, the commas in this sentence. So the selection is still there. So the reader will be able to find this sentence, and later the reader will be able to find the embedding features. As I have told you, we need two types of features. The first type is robust features. We want our selection to stay there. So for this fact, we use the robust features for selections, and we want them hard to be undone by the attacker. For that, we are now currently using like words or the verb classes. The yielding features are the ones that are easy to change. For that, we are using them for embedding the watermark bits. And again, like, this work appeared in a paper at ACM Multimedia Content Protection recently, in fact, last year. And you can see details of it here. This is a very small snapshot to show you like a little bit more detail about it. This is a system that we have built. It is using Xtag parser is an outside tool, outside resource, WordNet and RealPro for generation. And the middle ones are like the ones that we have developed. So given this sentence at the top, he said Canada and Britain recently rejected the idea, this system can automatically rewrite it as he said the idea was recently rejected by Canada and Britain. Let's move on to the other ones, the other systems that we have developed. Here, our aim is to make it hard to undo the embedding changes. We have used the hiding virtues of ambiguity. So when you speak ambiguous, people can get different meanings from what you have said. So we wanted to lower the adversary's power. So we thought if we increase the adversary's uncertainty about the original text, we can achieve this lowering the power of adversary. And please keep in mind that we assume that the adversary is a machine, not a human reading the text. Because at that point, our systems assume that the adversary has spent the time to rewrite the text. And we have used knowledge asymmetry between the embedding process and the adversary. For example, this is a term that I learned in US, Go boilers. And it can come from any of the synonyms of Go. It can be belong boilers, it can be survive boilers, it can even be die boilers, because it is the same in the same synonym set of Go. So it is harder for a person who is hearing Go boilers to decide where it came from. So we are depending on this knowledge asymmetry. And we call these type of transformations computationally asymmetric transformations, where performing the transformation one way is easier, but when you want to reverse it, you need a disproportionately larger computational resource or a human intervention. And we use robust synonym substitution, which is one of the computational asymmetric transformations. For example, I'm given the sentence, the robot is very smart. The meaning is very clear here, but if I change it to the robot is very bright, the attacker is confused. Is the robot polished or smart? Because in its database, it thinks that they are both the synonyms of the word bright. Again, this appeared in a paper that you can find details at ACM Multimedia Security. I want to tell you again a little bit about what is behind this EcoMark system. What we do is we build a graph out of a given electronic dictionary, say WordNet. The graph is the word and the senses. Sense means a meaning, and every word can